So this semester we will go over to the 506, that is the second part of the electromagnetic theory. So I understood that from the interview of each of them, you have different backgrounds. So some of them you go over the chapter 6, that is the Maxwell's equations, and chapter 7, propagation of the electromagnetic waves, reflection and refraction. But some of them didn't do in the past. So I'll go over quickly. Quickly means that in 1 or 2 weeks, chapter 6 and chapter 7, that will be the Maxwell's equations, gauge and wave equations and conservation laws, and we will study that the reflection and refraction of the electromagnetic waves. So let us start with chapter 6, that is the Maxwell's equations. So all you know the Maxwell's equations well from the undergraduate and the first part of the course, and let me remind you once more. So source of the electric displacement is the charge density, and the source of the magnetic field is the current density and the change of the electric displacement in time. And Faraday's law relates that the change of the change of the magnetic flux density with the electric field and or electromagnetic force. So in the differential form, that is the curl of E plus del B over del T is equal to 0. And the last equation tells you that del dot B is equal to 0. That means that there's no magnetic monopoles. So in the first part of the, let's say that this was known Ampere's law, and that was critical in the first derivation. This wasn't there. So del D over del T wasn't there, and Ampere's law was saying that the H is due to the currents. But there is a problem in this equation. Do you remember that what was the problem in that equation? So basically, no. Basically, this without this doesn't the continuity equation. That is the problem. So you will have continuity equation time to time in quantum mechanics and here, but if you have problems in the continuity equations, you have to be careful. This is valid in the relativistic quantum mechanics also. So if you take the divergence of curl of H, you know that this should be 0. But if you look at the right hand side, according to that, del dot J have to be equal to 0. Del dot J is equal to 0 if you are in magnetostatic or electrostatic. So if you have time varying fields, you have to satisfy the continuity equation. And what the continuity equation? Del rho over del T is equal to 0. So does it satisfy in this form? Yes. How? Because I know that the rho is equal to del dot T. And so if you take this equation, so let me go, del dot J plus and the divergence of del over del T, you can replace that derivative operator with the divergence. And from the first Maxwell's equations, that is equal to rho. This term is equal to rho. And this tells us that del dot J plus del rho over del T is equal to 0. So as you see that Ampere's law alone means that the source of the magnetic field is the current density, does not satisfy the continuity equation. And another source of the magnetic field is the change of the electric displacement in time. So in practically, you know this from the freshman physics. So from the freshman physics, you know that the RC program, when you are charging the capacitor, what you have? Current. Since you have current, you have some magnetic field around the wires, okay? Some magnetic fields. But if you took the Ampere's law alone, when you look at the inside the capacitor, you shouldn't have any magnetic field. So magnetic field should drop to zero sharply. But this is not the case. There's a magnetic field inside the capacitor. And the source of the magnetic field inside the capacitor is the change of the electric displacement. While you are charging the capacitor, current is changing, and what you have? You have electric field inside the capacitor, and that is changing because the amount of the charges in the place are changing. So if you have this alone, your magnetic field structure should be something like this. You have a B, and then it drops to zero in the capacitor and go up. Physically, it's not good. Because why it is not good? We have a sharp change. We have a discontinuity on the field. So, and observationally, you have a magnetic field in the capacitor. So basically, we have 4 Maxwell's equations. Let me tell you again. Source of the electric displacement, D, is the charge density. Source of the magnetic field is the current density and the change of the electric displacement in time. We have the Faraday's equations, and that tells you that how when the magnetic flux change in time, you produce an electromotive force if you have any closed loop. Let's say if you have any closed loop, and if you put this to the external magnetic field, change the flux, you will have some current, induced current. Change the area of the loop, you will again obtain some current. And we don't have a magnetic poles. Delta B is equal to 0. So there are some exercises. For example, if you look at the some chapter in Griffiths, if you introduce a magnetic monopoles, you have to fix the other Maxwell's equations. Why? You have to satisfy again the continuity equations. So you can go and look at the Griffiths third year's book. Now, these are the Maxwell's equations, and let us look at the Maxwell's equations in terms of potentials. We have 2 potentials, vector potentials and scalar potentials. So vector and scalar potentials. So tell me, looking at this, del dot B equal to 0, what kind of potential you can generate such that the del dot B equal to 0. So B could be what? So the answer is, you know, and easy. If you define that the B is a curl of E, divergence of curl of E will be 0. Like here, divergence of curl of H is 0. So this is the mathematical. So if you have a vector, and if you take the curl and take the divergence, that will be 0. So therefore, you can generate the B as a curl of something, and that something is the vector potential. What I am trying to do, I am trying to express these Maxwell's equations, some potentials. You know that the Coulomb's law, there's an electrostatic potential in electrostatic, and we in the Maxwell's equations, one thing, del dot B is equal to 0, and that tells us that the B should be curl of E. And what equation we can use for defining the potential. So pick up the Faraday's equations. We have the Faraday's equations. Now B is curl of E. Okay, we defined. And insert this to the Faraday's equations. What you are going to obtain in the Faraday's equations, curl of E plus del over del T, curl of E is equal to 0. So put everything in the curl parentheses. You will get curl E plus del E over del T is equal to 0. How you can satisfy this? How you can satisfy this condition? You can satisfy this condition if this function is the gradient of some scalar function. So calling this gradient of some scalar function, let me put minus sign, then that tells you that your electric field could be written as minus gradient of the scalar function minus del E over del T. So these are the description of the electric field and magnetic field in terms of potentials. One is the scalar potential, the other is the vector potential. So after introducing the fields, we can look at these fields are the same in some different choices of the potentials. So you have some freedom to choose the vector potential and scalar potential such that the E and B doesn't affect it. We call these kinds of transformations gauge transformations. So the rule is the following. So choose the vector potential a little bit change as E plus gradient of the some scalar function, and choose the scalar potential is a change of the in the following form. If you change the potentials in that form, you can automatically see that E and B fields doesn't affect it. So that is very simple. B prime is equal to, in our new choice, is equal to curl of A prime and you know that the curl of the gradient is 0. So B doesn't affect it under this transformation, and the name of this transformation is the gauge transformation. And you can do the same thing to the electric field. So if you look at the electric field under this transformation, and all you have to do, substitute instead of phi and instead of phi prime instead of A as A prime, and what you are going to obtain? Minus gradient of phi prime. Where is my phi prime? That is phi minus del scalar potential due to the gauge transformation. That term, that is the phi prime. And what I need, minus del over del T A prime. Where is my A prime? A prime is equal to, is there. So that is A plus gradient of some scalar potential. So if you look at here, minus gradient of V minus del E over del T A is our E field. And if you look at the other mixture, you have minus plus gradient of del potential over del T, and what you have minus plus, you have what minus plus, and the order is changed. So this gradient times del over del T commutes each other. Therefore, the rest will be the 0. So basically, you will get plus gradient of del over del T minus what del over del T gradient of the some scalar potential. You can interchange the order, and that will be cancelled out, and you will get what E equal to E prime is equal to E. So the bottom line, the potentials are not unique. At certain transformations, they give us what? Same electric field and magnetic field. And the name is called gauge transformations. Now, we know that the gauge transformations, the property of the gauge transformation, fields doesn't affect it. So basically, E prime and P prime doesn't affect it. And we have the fields in terms of the potentials. The next things, put together these potentials into the Maxwell's equations and find the Maxwell's equations in terms of potentials. So let us go to the vacuum. Electric displacement is related with electric field. What is the proportion of the constant? You know, as a small epsilon, that is the permittivity of the space. So for vacuum, that is epsilon 0. And if you pick the first Maxwell's equation, that becomes del dot E is equal to charge density over epsilon 0. That is the first Maxwell's equations. And I know the electric field. So this is the electric field. Divergence of minus gradient of V minus del E over del T is equal to rho over epsilon 0. Now the things are mixing. So you have one equation in terms of scalar and the vector potential. So altogether, this becomes divergence times divergence of the gradient is the Laplacian of V minus del over del T. You can replace the order of the operations. So that becomes del dot E, and that is equal to rho over epsilon 0. So this is divergence of del E over del T, but del over del T and the divergence are replace each other. You obtain this. So let us keep this equation. Maybe call first equation. So at the moment I will say something. I derived at the electric field and magnetic field using which Maxwell's equations? So basically 4 sets. So 2 of them has property of what? 2 of them has the property of what? Source. The other has no source. These 2. So we derived at the potentials with the Maxwell's equations without any source. Now we are playing with the Maxwell's equations with the source. Because the potential informations are taken from the source-free Maxwell's equations. and the fields are generated from the source-free Maxwell's equations, and they are inserted to the Maxwell's equations with the source. So basically, I am using all Maxwell's equations. So this is one equation I have, and the other Maxwell equations with the source is I discussed this one. We call as a modified Ampere's law also. So let me start to study somewhere here. So somewhere in the middle. So I have curl of H, that is current density plus del D over del T, and H is equal to, for free medium, is B over mu 0, and we have current density del over del T epsilon 0 D epsilon 0 E. So instead of B, write the B in terms of potential, namely vector potential, curl of A, multiply mu 0, that will be to the right hand side, that will be mu 0 current density, and this will be mu 0 epsilon 0 del over del T, and the electric field, and electric field is equal to minus gradient of scalar potential minus del E over del T. So this is the representation of the second Maxwell's equation in terms of potentials. So do you know what is mu 0 epsilon 0? Mu 0 epsilon 0? 1 over c square. And the other thing, you need the curl of a vector. So you have, maybe you derive in some mathematical courses, it is in the book, first page, so I will directly write the result. So that is equal to what? Gradient of divergence of A minus Laplacian of A. Put the all stuff here to the left the current density on the right. So the things will be the following: minus 1 over c square del over del T minus gradient of P minus del E over del T, that is equal to mu 0 current density. So I left the current density on the right, pick up the things to the left. So some organization, put this equation to the following form. Multiply minus both sides and pick up the Laplacian of A to here. And somewhere you have what? Minus minus plus. And if you multiply with minus, that will be minus. That is 1 over c square del square over del T square. So that will be the other term. 1 over c square del square A over del T square. Do you remember what piece is this? Do you remember the piece of this equation? Wave equation, yes. So then you have the gradient here, somewhere you have the gradient there. So take the gradient parenthesis. You have divergence of A plus 1 over c square del scalar potential phi over del t. Since I multiply everything with minus, that would be mu 0 times the current density. So this is correct. And let us look at this term. If you change the order, take the gradient outside, this is positive, but multiply minus all the left and right, that will be minus again, and you will get gradient of that term. So that is the second set. This is the second set. And as you see, that first and the second equation coupled each other. How they are coupled? One has the phi and vector potential, other also phi and vector potential. So one choice of fixing this term is 0. Put these two equations as a decoupled. If I say that this term is equal to 0, what kind of equation you obtain? As your friend says, left-hand side is wave equation, but the right-hand side something. This is non-homogeneous wave equation. And if you fix this as a 0, this equation could be in the nice format. So basically, what is done is the following. Del dot E plus 1 over c square del phi over del t is equal to 0. Do you know that this choice is a name? Do you remember? Lorentz condition. So this is well-known Lorentz condition. Under this condition, this becomes, second becomes non-homogeneous wave equation. That is equal to minus mu 0 current density. First one, look at the first one. You have what? Divergence of A here. And the divergence A is equal to minus 1 over c squared del phi over del t. If you plug this information to here, you will obtain what? So under the Lorentz condition, what will be this term? Del dot A will be 1 over c squared del phi over del t. And this becomes del phi squared over del t squared. So this equation turns to be again non-homogeneous wave equation, but the two equations now decoupled. Above is in terms of vector potential, below is in terms of the scalar potential. Sources are different. The above has the source is the current density, and the below one will have the source is charge density. So the second set will be del square phi minus 1 over c squared del phi square over del t square. And the source is the charge density. So these two equations are containing all informations of the Maxwell's equations in terms of potentials, vectors and scalar potentials, but under this condition, which is called Lorentz condition, they decoupled. When they decouple, we can also easily solve. So let me write the Lorentz condition. Del dot E plus 1 over c squared del phi over del t is equal to 0. In the later parts of the course, towards the, let me say it, after the half, when we study in terms of relativistic, these equations will, as a form, will be covariant in any inertial frame. So forms will not be changed. Now the next thing, do you know how to solve this equation? Some of you see, some of you. So did you see? Did you solve this? Okay, now let me look at what is going on to the Lorentz condition under the gauge transformation first, and then I will define that another gauge which is called Coulomb gauge. So this is the Lorentz condition, and another one will be the Coulomb gauge. In that case, delta E will be equal to 0. But before going to do this, let me clean some parts, maybe most parts, and to look at the Lorentz condition under the gauge transformation. So we have del dot E plus 1 over C square del P over del T is equal to 0. So what I am going to do, I will write E as a E prime, Phi as a Phi prime in terms of the gauge transformation. So the situation is the following. Divergence of A, instead of A, E prime is E plus gradient of some scalar function 1 over C square del over del T Phi minus del scalar potential, some function scalar potential over T. If you arrange the terms, what you are going to obtain? You will obtain divergence of E, and the other term plus divergence E plus 1 over C square del Phi over del T. That is the Lorentz condition on one side. On the other side, you will obtain, I think, Laplacian of the some scalar potential minus 1 over C square del square over del T square. So did I put the sign is correct? Divergence of E, this is there, this goes at the other side as a minus, and this goes at the other side as a positive. So I know that from the Lorentz condition this should be 0. Therefore, our gauge in the gauge transformations should satisfy what? So we are saying that A prime could be written as A plus gradient of scalar potential, and what is the other one? Phi prime was Phi minus del scalar potential over del T. And what equation is this? It is wave equation. So if you introduce a gauge transformations, your gauges should be satisfy the wave equation. So this should be 0 if the left hand side is equal to 0. Now let us move on the more complicated part as a view. There is another choice. The nice thing in the Lorentz condition, you have the Maxwell's equations, but you decouple the potentials. And you can solve these potentials with the help of the non-homogeneous wave equation. I will study it in the next hour, and we will define the Green's function, and we will solve this in the next hour. But before going to do, Let us look at the other condition. So can I erase this part? Now let us look at the other condition. Look at the first equation and the second equation and tell me that on particular choice, you know the solution already. The particular choice of the fixing this as a 0 brings you the two non-homogeneous wave equations. The solution is known. I will show you, but it is known. But if you look at these two, there's another particular choice, and if you choose that choice, you already know that one of the solutions, at least, scalar or vector potential. What could be? This one, this one. First one. So what you are going to choose? Divergence. Yes. If you say that divergence A equal to 0, this turns to be Poisson equation. You know that the solution. You studied this in the first part of the course several weeks in different techniques, okay, in different coordinate systems, okay. And if you say that this is equal to 0, that is called, what is the name? What is Coulomb? Why the name is Coulomb? Because that gives you the Coulomb potential, okay. So choosing the del dot E equal to 0 is called a Coulomb gauge. So if you say del dot E is equal to 0, we call this as a Coulomb gauge. And you can automatically write that the solution, because this is the Poisson equation, you know that the solution. So the solution should be what? 1 over 4 pi epsilon 0 charge density over x minus x prime integrated through the volume. And charge density could be depending on space and time, therefore your potential should be depending on space and time. So this is easy, but this is complicated now. Look at the second one. Second one, you will get rid of this, but you have this term. So next step is to play this equation. Put as something we know. Probably you haven't seen this in the past. So if you plug the Coulomb condition gauge del dot equal to 0 here, you will end up the following equation. Laplacian of A 1 over c square del square A over del t square is equal to minus mu 0 current density, and what we have, the terms goes to the other side, 1 over c square gradient of del phi over del t. So this second equation turns to be this, okay? Now we have potential, scalar potential, we have vector potential. This is a little bit in the complicated situation. Now, what I am going to do in the Coulomb gauge. So the usual trick is the following. The usual trick is the following. The current density could be written in two forms. One is the translational The other is the longitudinal. So as an example, for longitudinal means that if you have a very long, infinitely long wires, that is the longitudinal current density. For translational current, transverse current density, transverse current density, what could be the transverse current density? Solenoid or antenna. Okay, you can decompose. The property is the following. One of them has the divergence equal to 0, the other has the curl is equal to 0. Which one is what? So one of them.
Is for transverse.
Yes.
It's like one normal.
Yes. Yes. This one for longitudinal curl. It is not rotating to itself. So curl is equal to 0. So basically the property is the following. Curl of JL is equal to 0, and for that one divergence of JT is equal to 0. This is one property. And I can write the G is GL plus G transverse. And I could save you the result in the beginning. I will play this term, and I will show you that this term is related with the mu0 times JL, longitudinal. And there will be cancellations, and this turns to be non-homogeneous wave equations. So let us start to work, and then give a break. Let me start a little bit, continue, and then we can stop. So take the first, try to generate this term using the scalar potential. So take the time derivative. That is 1 over 4 pi epsilon 0 del charge density over del t 1 over x minus x prime d cube x prime using the continuity equation. Using the continuity equation, you can write what? Del rho over del t is minus divergence of J both divergence and J depends on the what? Primes. Okay, because source was depending on prime. So maybe I should put a prime here, and let me say gx prime t times 1 over x minus x prime d cube x prime. So I generated del phi over del t, then I will multiply with the gradient. I will take the gradient, sorry, and 1 over c square. This term will be gradient del phi over del t is equal to minus 1 over 4 pi epsilon 0 c square gradient with respect to the x divergence of x prime dot current density divided by x minus x prime integrated d cube x prime. So this will be that. And what is next? So 1 over c square is, you know, 1 over mu 0 epsilon 0, so epsilon 0 is cancelled out, and that is in that form. So look in here, and we have the divergence of G, and if it is not 0, what kind of current you have here? Divergence of transverse or divergence of longitudinal? Delta G transverse is 0. If you have non-zero, this should be longitudinal part, because that will be non-zero. But that is something there. So what is this? So next thing I am going to show you that that term is nothing but mu 0 JL. This is mu 0 goes up. In the parentheses, you have 1 over 4 pi divergence of current density x minus x prime d cube x prime, and I am going to show you that there is a t here, x prime t d cube x prime, and this is nothing but JL. So maybe after the break I can show. So if this is JL, your result will be what? The important part is the result. If you call the right hand side is mu 0 JL plus J transverse, and if this term, I am telling you that will be JL, this term will be cancelled and the right hand side will be what? Mu 0 J transverse. Okay, so in the next hour I will show you that this is equal to JL. This is an easy derivation, but some calculus we will use, so you can remember that the first part of the course when we use that simple calculus. But what does it tell us, this equation? We have the non-homogeneous wave equation, and the source of this non-homogeneous wave equations is the transverse components of the currents. So in the Lorentz gauge, you have the full current density and the full charge density, but in that case, you will end up the non-homogeneous wave equation, but the source of transverse current density. Which gauge we are working on? Coulomb gauge. For potential Poisson equation, but for the vector potential, we have the non-homogeneous wave equation again, but the source is the transverse. So this Coulomb gauge is also called a different name due to this current. What kind of current we have? Transverse means that the solenoidal or antenna oscillating currents. So this gauge is also called radiation gauge, because basically vector potential you obtain from the solution could be used calculating the magnetic field and so on, but it is due to the radiation because the source is what? Transverse, some oscillating source back and forward. So after the break, I will show you this is indeed the longitudinal current density. Then what we have to do, we have to learn how we solve that the non-homogeneous wave equation. Okay, so in Lorentz condition we have two non-homogeneous wave equation, and here we have one here, and in the other applications when we study the scattering and so on, we will come to so often to the non-homogeneous wave equations, and we have to know that how to solve the non-homogeneous wave equation. So after the break, we can continue.